Hello, welcome to our term project presentation, and this is group 15, and our topic is Spatial-Temporal Graph Neural Network for Dynamic Wind Power Forecasting. And our group include Han Jingdong, Chen Hehua, and I am Li Gen. So let's get started. And first, let me give you some background introduction. So wind power generation means getting the electric energy by converting wind energy into rotating energy of the blades and converting that rotating energy into electric energy by the generator. However, the wind power generation it cannot be produced consistently because the generation process can be significantly affected by many factors like weather conditions, internal situations, and the nearby turbine, which are causing high temporal instability. And wind power forecasting aims to accurately estimate the wind power supply of a wind farm at different timescales, which means that after forecasting, we can know when the power generation rate is high and when it's low so that we can better manage the whole power supply system. And the current WPF studies merely utilized time series information but neglected relations among different wind turbines. And recently, graph neural network has been widely applied in many fields. And different from CNN, GNN could handle long Euclidean data, and this is able to model more complicated relations. So a graph represents the relations between a collection of entities. So a graph data should contain three types of information as shown in the three figures. So the first one is the vertex or node attributes, and the second one is the edge attributes and directions, and the third one is the global attributes. So many data can represent into graphs, like as shown in these four figures: images, text, moleculars, and social networks, and many other data can both represent into graphs. So in this project, we propose a novel model from a multi-graph, multi-task perspective to achieve spatial-temporal WPF. And next, let's see what our dataset looks like. So in this study, we use a unique set of spatial dynamic wind power forecasting data, SDWPF. And the SDWPF dataset is sampled every 10 minutes for each turbine in a wind power farm. And in this dataset, it totally contains 134 wind turbines. And this table is what the dataset look like. So from this table, we can see that the dataset record those variables every 10 minutes for each turbine. And let's see what every column means. So the table 2 is the column names and their specifications of this dataset. And generally, the dataset mainly contains two kinds of variables. The first one is the external characteristics that have an important impact on the wind energy production, like the temperature, wind speed, and wind direction. And the second kind of information is the internal variables, like the pitch angle, nacelle direction, and others. And our target variable is the active power. So additionally, the relative position of the turbine in the wind farm are also provided so that we can study the spatial correlations and the spatial distribution of those wind turbines are shown in this figure.
Okay, then let's move to the methodology part. And in our project, we utilized 5 baseline models. And the first one is called moving average. And the basic idea of moving average is to predict target values by averaging previous data points. And the second model is called auto-regression integrated moving average. And it is a very classic statistical model and is proved to be quite powerful in time series tasks. And the third one is called random forest. And the basic idea behind random forest is to bag thousands of decision trees together to predict the target values. And these three baseline models are traditional machine learning models. And here, the next two models, they are both related to deep learning methods. And the fourth one is called gated recurrent unit, one of the most popular recurrent neural networks. And in GRU, there are two gates, update gate and reset gate. And both gates determine how much new information should be recorded and how much old memory should be forgotten from the previous hidden states. And the last baseline model is called Spatio-Temporal GCN. And because in our data set, it includes the location coordinates, so we can directly build a neighborhood graph based on the data set. And afterwards, we can just put the neighborhood graph into GCN model and aggregate the spatial information from the locations. And then we can just feed the information into GRU and to predict our target values. After talking about the baseline models, then I'm going to introduce the model we proposed in our report, which is called multi-graph multitask model. And we designed that model from different graph views and utilized various tasks. And actually, there are two modules in that model. And the first module is called the multi-graph module. And we constructed two graphs from different views. And the first view is called neighborhood graph, just as a fifth baseline. In that graph, each node is a corresponding wind turbine. The entry in the adjacency matrix is actually determined by the distance among different wind turbines. And specifically, if the distance between two turbines are too far, we just treat the weight as 0. And the second graph is called context graph. And here we introduce two learnable matrices, C1 and C2. Multiplication of these two matrices can be used to generate the matrices of the context graph. And afterwards, we just put these two graphs into GCN module and to generate the turbine representation matrix. And the second module is called multitask module. And so, as the slide shows, the main task of our model is to predict the future wind power. However, previous studies proved that with introduction of some auxiliary tasks, the performance of the model can be further improved. And specifically in our model, we also trained the model to predict the wind speed. And afterwards, we can just acquire the future laws via weighted sum. That is the basic introduction of our methodology. Thank you.
Next, I will introduce the experiment part. Here is the overall performance. The following table shows the overall performance. In the experiment, we use 5 baselines, 3 statistical learning baselines, and 2 deep learning baselines. Here we use mean square error as the evaluation matrix. From table 2, we can see our model MGMT outperforms all the baselines, which indicates the superiority of the proposed model. Besides, we also observe all deep learning approaches have a comparable or better performance than traditional models because deep neural networks can deal with complicated spatial-temporal dependencies. Besides, MA performs relatively poor because they fail to model the complex correlations in spatial-temporal data. ARIMA has a comparable performance with deep learning methods. The possible reason, I guess, maybe ARIMA is robust and it can handle the high uncertainty of wind power. After that, we also evaluate the effectiveness of each component of our proposed model. We first test the effect of multi-graph convolution module. Specifically, we evaluate 3 variants of our model. RNC removes either neighborhood graph and context graph. RNG remove neighborhood graph and RCG remove context graph. The results are reported in the table 4. We can see removing a neighborhood graph or context graph will lead to a performance degradation, which demonstrates the effectiveness of the proposed multi-graph convolution. In the experiment, we jointly train the wind power prediction task together with 2 relevant tasks, including reactive power forecasting and wind speed forecasting. Table 5 shows the effect of multitask representation learning. We compare 3 variants of the proposed model. MAIN means only use mean wind power prediction during training stage, and WSF means only employ wind speed forecasting as auxiliary task, and IEP means adopt reactive power prediction as auxiliary task. From table 5, we can see a performance gain by adding either wind speed forecasting or reactive power forecasting into our model. So we can conclude that multitask learning can help us avoid overfitting and lead to better performance. So overall, we summarize our work. Our task is to forecast the future dynamic wind power in a wind farm. Here we have 2 challenges or properties. First is the spatial-temporal correlations among wind turbines. And second is the latent relationships between different variables. To address the above challenges, we develop a multi-graph convolution to model the different types of spatial correlations. And we also develop a multitask representation learning to further enhance the model generalization ability. Yes, that's all our presentation. Thank you.